Okay, we are recording. So, very first class, very first day of review. There are a couple of things that we need to kind of get out of the way so we can discuss algebra. And those concepts are what a set is, actually a very straightforward concept. But then we introduce the whole mathematical way of writing it, which can even get confusing to someone who's sitting in the living room over here who has an engineering degree. And I did something silly on Facebook. I put a set on Facebook, and he came and he asked me, he had a question about it. And I'll explain to you when we get there in a few slides what the question was, because it can be confusing even to people who've been doing this forever. So we're going to talk about what a set is and then how to write it mathematically, because you're in a math class and we have to be able to start dealing and having our brains work mathematically. So we'll talk about how to write a set using mathematical terminology. It really isn't that hard. It just, you put some symbols in there and you're good to go. And then we'll talk about what a subset is. And once we talk about a subset, we can start dealing with all the number systems except one. There's one number system we're not going to talk about today. We'll talk about later in the course. But we can talk about all the number systems that we use in arithmetic and algebra, except one. All right. So at the end of this review, we're going to be able to write a set using a description, and that's something you're already doing all the time. If I ask you, do you have a set of something? You could say to me, sure, I have a set of Barbie dolls. Maybe I collect Barbie dolls. Or a set of dishes. I have in my cabinet a bunch of dishes that actually match. So I could call that a set of dishes. So that's something you already do all the time. But then we're going to talk about how you could describe that set using a roster. And what's a roster? If I tell you that I have a roster of names for this class, then you know it's just a list, and that's all a roster is. So if I describe a set using a roster, I list the things inside that set. And then we got to get the mathematical thing. And the mathematical thing is called set builder notation. It's a special notation we use in mathematics. And when you see that notation as a student or a mathematician, you know immediately, oh, that's a set. So there are things that we use, notation that we use all through mathematics, algebra, that we immediately know when we see that notation that it means this mathematically. So we'll talk about that. And then at the end, we'll describe the number systems, all the different kinds of numbers, except one system that we use in algebra. There's a particular number system that we have to get later to take care of a special instance of stuff that we do. And the reason that number system was invented is because we needed to take care of that one particular situation. We'll talk about that later in the regular class. Okay, so what's a set? A set is just a collection of things. It's a collection of objects. And so those objects that are in this set, specifically in mathematics, we call those elements. You could also call those members of the set, but we typically use the word elements. So we have a picture there, and that is a T set. That T set consists of objects, and those objects are the elements in that set. So what are the elements? Well, there's a tray, there's a teapot, and there are 4 teacups. So that set descriptively, its elements are a tray, a teapot, and 4 teacups. Okay, so that's what a set is. It's just a collection of objects. So you have 3 different ways that you can describe a set. The first way I described that picture was, it's a tea set. Okay, maybe that's not descriptive enough. So I listed a roster, a list of the elements in that set. I said that set contains a tray, a teapot, and 4 teacups. So that is a roster. It just lists the items that are in that set. Now, set builder notation, it's really not practical for this particular set. So we'll talk about that in a minute. We'll leave that behind. But that's another way. It's a truly, purely mathematical way of describing your set. All right. So what would be a description of this set? So there are 3 ways you can list a set. You can describe it. You can list the elements, which is basically what we have here. We have a roster. We have all the elements in the set. Or you could use set builder notation. Let's just describe it. What description would you give of this set? This is a set that contains the elements January, February, March, April, May, June, July, August, September, October, November, and December. What would be your description of that set? You can put in chat, you can take yourself off mute, or if you pause long enough, I'll answer the question.
It's a description of the months.
It's the months and the year. Exactly. So to describe the set that you have a list of the elements, you could describe it just as the months of the year. All right. So that was a list, but it wasn't a formal mathematical list. In math, if we list the elements of a set, we call that roster form. And we list those elements inside of things called braces. So let me get my iPad over here so I can write on it. So these things right here are called braces. And on your keyboard, they're up above the enter key. They're shift above the brackets. So when you see things listed inside a set of braces, a pair of braces, separated by commas, that is a set. I can't think of us using that particular nomenclature for anything else in math. If it's a brace and it's things separated by commas, that is a roster that describes a set. So for example, a brace, a 1, a comma, a 2, a comma, and a 3 is the roster notation that describes the set that contains the elements 1, 2, and 3. So if you see a list of items separated by commas inside braces, that is a roster description of a set. Now you could have numbers separated by commas inside other symbols, but that wouldn't be a set. So you could have a 1 and a 2 and a 3 separated by commas inside parentheses. And I really need to know the context of that. I'm pretty sure I know what that means in math, but I probably kind of need to know the context in which it was used. I'm pretty sure that's a point described in 3 space, in 3 dimensions, I think, but I really have to know. And then the brackets, 1, 2, 3, I'm not sure what's that's referring to. I don't know right off the top of my head. I'm sure there is a mathematical interpretation of that, but I don't know what it is. So if I see numbers separated by commas inside braces, I know that's a set. Well, we got some animation issues here. All right. So how do we name sets? In math, typically we use capital letters to name sets. So we have a definition here of the natural numbers. And the natural numbers are the numbers you count with. Now, my adorable, and he is adorable, 2-year-old grandson can count. He can count up to, I don't know, 5 or 10. He can count up pretty high. But where do you start counting at? You start counting at the number 1, and that's because you have fingers and thumbs on your hand. And that is typically how human beings start to count. So if we ask him to count, he either takes a finger and points to what he's counting at. There's 1, 2, 3 dinosaurs. But where does he start counting? He starts counting at 1. Or if he uses his fingers, 1, 2, 3. He uses his fingers to count. So we always start counting at 1. Now, if you're ever going to be a computer scientist, if you decide to go into STEM and become a computer scientist, they argue with me that no, counting starts at 0. That's a computer science definition. It's not a mathematical definition. So the numbers that we count with are called the natural numbers. And the natural numbers start at the number 1 and continue indefinitely. So we use the capital letter N, and then an equal sign, and then the brace, and then a roster of, or a list of the numbers, and then set of natural numbers. Now you'll notice at the end of this set, we have a 1, a 2, 3, a 4, and a 5 separated by commas. But at the end, we have what is called an ellipsis. That's your Jeopardy word of the day. And what does an ellipsis mean? What it always means, that it just goes on. So the set of natural numbers continue on indefinitely. And we say the set goes towards infinity. And infinity is a concept, it's not an actual number. But the natural numbers continue to go to the right indefinitely. And as children, you see that children learn to count. They first learn to count to like 5, and they're very proud of that. And then they go to 10, then they go to 20, and they go to 30. So they continue to the right in their learning of counting because counting continues. It continues forever and definitely to the right. And that's what the ellipsis means. Okay? So the number line is something that we use in mathematics to represent the number systems that we're interested in. And it's arranged in numerical order from left to right. That's the way we read, and that's the way mathematics works, no matter if you read from left to right or right to left. Mathematical numbers go from smaller to larger from the left to the right. And the set of numbers represented on the number line continue indefinitely both to the left and to the right. So the natural numbers, which is the number set we just talked about, starts here at 1 and continues indefinitely to the right. And just looking at the natural numbers, I can determine the numerical order of those numbers. I can see from my number line that 3 is bigger than 2 because 3 is to the right of 2, so we're in numerical order. So 4 is bigger than 1 because 4 is to the right of 1 on the number line, and that is how order works. If the number is to the right of the other number, it's greater than that number. If it's to the left, it's less than. So 2 is less than 5. 2 is less than 5 because it's to the left of 5 on the number line. If we go in numerical order, and we're only looking at natural numbers, 1 is the smallest, 2 is the next biggest, 3 is the next biggest, et cetera, et cetera. So we increase by 1 each time. We increase. The numbers get bigger by 1 as we go to the right. I pretty much said that. All right. All right, so that leads us to the discussion of inequalities, if my PowerPoint slide will go back. So since we know we have a number line, and typically the number line, we have 0 in the middle, and we have the positive numbers to the right of 0 and the negative numbers to the left. Negative numbers are smaller than positive numbers. You know for a fact that -4 degrees Fahrenheit is colder than 0 degrees Fahrenheit or 40 degrees Fahrenheit. So there is a scale from smaller to larger. So negative numbers are smaller than positive numbers by their nature and by the number line. So looking at the number line, we can start looking at inequalities. Is something bigger or smaller than something else? So that first symbol on this slide, where we have that arrow pointing to the left, that indicates less than. So we can actually put numbers on each side of this symbol to show that relationship between numbers on the number line. So we could say something like 2 is less than 3. And 2 is less than 3 because 2 is to the left of 3 on the number line. In numerical order, 2 is smaller than 3. So we have that relationship that 2 is less than 3. Or we could say 1 is less than 5, looking at the natural numbers. And the reason that is because 1 is to the left of 5 on the number line. In numerical order, 1 comes first, 5 comes later. Okay, if the arrow points to the right, that means greater than. And I know there are teachers who say the arrow always points to the smaller number, and that is true. So in that first example, less than, the arrow is pointing to the number that's smaller of the two. It's 2 is less than 3, it's pointing to the 2. 2 is smaller than 3. It's pointing to the 1. 1 is smaller than 5. So greater than, we could write 10 is greater than 5. And the reason 10 is greater than 5 is because 10 is to the right of 5 on the number line. So in numerical order, 5 would come first and then 10 would come later. So 5 would be the smaller of those two numbers. So 10 would be greater than 5. You could also write that as 5 is less than 10. It means exactly the same thing. They mean exactly the same thing because the arrow is pointing to the 5, which is the smaller of that group of two numbers. Or you could write 1,000 is greater than 5. 1,000 is greater than 5 because 1,000 is to the right of 5 on the number line. Or you could write 5 is less than 1,000. It means exactly the same thing. Now, if we put a bar underneath it, that includes equality. So this means less than or equal to. And there are instances in algebra when we care if something's less than something else, or is it equal to something else? And that's what that means. It's less than or it's equal to. So you could write 2 is less than or equal to 3. That is true. 2 is less than 3. So it satisfies that less than quality of that inequality. Or you could write 2 is less than or equal to 2. That is true. 2 isn't less than 2, but 2 is equal to 2. So is it less than or equal to? Yes, because 2 is equal to 2. And then this is greater than or equal to. So we could write 3 is greater than or equal to 3. It's not greater than 3. 3 is not greater than itself, but it is equal to itself. So you could write something like that. Okay. So now that we've looked at inequalities and we've looked at how we can describe sets using a roster, let's take those two and combine them, and let's create a set and write it in roster form from a description. So we say set A, so I'm going to write that down. Set A is equal to, and I'm going to open a brace. What is it equal to? Okay, let me get this. Pause just a second. Let me make sure. I'm trying to, as I let someone come in to make sure I count them present. There we go. All right, let me save that. Okay, so back to our slide. We have in a description that set A is the set. So I have that written down. A equals a set, open to brace, of natural numbers. The natural numbers start at 1, less than 6. Okay, 6 is over here somewhere. What are the numbers on the number line that are less than 6? And there are natural numbers. I mean, there are a whole infinite number of numbers that are less than 6. But of the natural numbers, what numbers are less than 6? What have you got? A 1, a 2, a 3, a 4, and a 5. We don't include 6 because 6 is not less than itself. So what numbers in the natural number system are less than 6? The numbers 1 through 5. So we've taken a description, the set of natural numbers less than 6, and written a set in roster form. And again, roster form means we just list the elements in that set. So those 5 numbers, 1 through 5, are the elements in the set of natural numbers less than 6. Okay, how about this one? B is the set of natural numbers less than or equal to 45. Now, to list this in roster form can be somewhat interesting because what set of numbers that are natural are less than 45? Well, 1 less than or equal to 45. 1, 2, 3, 4, 5, 6, 7, 8, 45. So there are a lot of numbers that are less than or equal to 45. Okay, so where do the natural numbers begin again? They begin at 1, and then we're going to go to 45. So those are the numbers that are going to be less than or equal to 45. So the way we typically do this is we list a couple of elements in the set. So 1, 2, and 3 are natural numbers that are going to be in this set. And then we put an ellipsis, and then we put a comma, and then we put the 45. So what does that mean? That means there are a bunch of numbers between 3 and 45 that are in this roster. 4, 5, 6, 7, 8, 9, 10, etc. But that would be too cumbersome to write as a list. So we kind of do this shortcut where we put the ellipsis in between a couple of numbers to represent all those numbers that we've left out of the roster. Just a shortcut way of writing this. And I do include 45 in this roster because it tells me that we're less than or equal to 45. So we are going to include 45 in this set because of the description that it's less than or equal to. Okay, a couple of more symbols that we need to look at. This is the Greek letter epsilon. There's your second Jeopardy word for the day. Epsilon. Can I spell it? I think that's correct. And we frequently use Greek letters in mathematics to represent certain quantities or certain things. And the Greek letter, and that's the lowercase epsilon. There's an uppercase too. but the lowercase letter epsilon represents is an element of. So for example, I could write that 2 is an element of the set of natural numbers. 2 is in the set of natural numbers. The natural numbers start at the number 1 and they continue on indefinitely to the right. Just like everything else in mathematics, if we put a line through it, we negate it. So if you put a line through the Greek letter epsilon, they're saying it's not an element of. So for example, -2 is not a natural number. The natural numbers are the counting numbers, start at 1 and continue indefinitely to the right. So we could write -2 is not an element of the natural numbers. It is not. It is an element of the numbers called the integers, which we'll talk about in just a minute. But it's not a natural number. Negative numbers are not natural numbers. Okie dokie. All right, so now let's get into our formal way of writing things in set notation in mathematics. We have to have a formal way of writing things. And that's not just to drive people crazy, although sometimes it seems that way. It's that we need to describe things, everybody in the same way, so that when you see that, we all know that we're doing exactly the same thing. It's why we have PEMDAS, parentheses, exponents, multiplications, and divisions left to right, additions, subtractions from left to right. We all have to do mathematical calculations the same way. And I see these, I used to get them on Instagram. I mean, my feed in Instagram would be one after the other of these people. What's the answer to this? And they'd give a little arithmetic problem. And you get so many incorrect answers. And that's because we're not doing the calculations the same way. We all have to calculate the same way. Otherwise, your plane's not going to fly. If one engineer calculates it one way and another engineer, I'm going to do my own thing in my arithmetic. Do you think that's a problem? I think that's a problem. So we all have to do things the same way. So set builder notation is a way of writing sets in a formal mathematical way, and we all do it the same way. So it's a concise and mathematical way to describe a set by specifying the properties or conditions that its members must satisfy. So the notation typically has the form a brace, an X, because the X represents any element in that set. So we introduce that concept in algebra that we can use letters to represent numbers. And that's pretty much what makes it algebra and not arithmetic. Because the fact of the matter is, the world varies. That is what it does. The world is not a static, not breathing, constant thing. It is not. Things vary. So it's important that we in mathematics, when we're modeling the world, that we say, hey, this is what varies. And I'm going to let this letter represent that thing, whatever it is, that varies. That's what algebra is all about. So we have the set of this X, something that varies, and that vertical line you see there means such that it's completely and totally translates to the two words such that. And then you give the condition of the set, either an inequality or say it's an element of or whatever. So here's for instance. So my son and his wife got married on 11/13/15. Now, there are those of us, and they're both nerds. They think that's kind of cool. They got married on Friday the 13th, November the 13th, 2015. And so he posted this on Facebook as a memory the other day. And so I wrote, because I'm a nerd. And the confusion I had from someone, my husband, was what that bar meant. He thought that was a capital I, and it's not. It translates exactly to the words such that. And that brings up the whole thing about mathematics, how it's important you understand the context of where you see this thing. And we'll talk about this a lot more later when we talk about logarithms, because holy moly, can you get in trouble with logarithms if you don't understand the context of the letters you see. We'll talk about that later. But he thought that meant an I, which meant integers. Well, we don't use I for integers anyway. In math, we use J. So J is the capital letter we use to represent these things we call integers. We'll talk about those in a second. And there's a reason, because we use I for something else. But anyway, that's not what that means. It means such that. So that's read the set of all x such that x is a natural number and x is between 11 and 15. And I think I probably should use less than or equal to's because I need to include 11 and 15. But that, I wrote something silly like that. And 2 people got it. 3 people got it. All right. So let's write a set in set builder notation. So we have the set B that consists of the numbers 1, 2, 3, 4, and 5. So how could we write that in set builder notation? Well, let's just get started. B is the set. So we're going to write B equals and open a brace, and then we're going to give it a variable name. And X is X is the typical variable we use in algebra everywhere, correct? Always use X and Y. Those are the 2 variables we use the most often. So we're going to use X here, and then we're going to put our vertical bar to represent the such that. And then we're going to describe the set using interval notation. We need to say that it's a natural number. That's always a good thing to do. And it is a natural number because the numbers 1, 2, 3, 4, and 5 are natural numbers. And then we could describe this. X is between 5 and 1. And that's what that means. That says that X is somewhere in between the numbers 1 and 5 on the number line, including the numbers 1 and 5. So what numbers are between 1 and 5 on the number line? 1, 2, 3, 4, and 5. Now you could also write it using inequality notation without the equals. So you could say something like, it's the set of all x such that x is a natural number and x is between, well, probably not, but we could write something like this. It's between 0 and 6. And I hesitated there. I said, probably not, because 0 is not a natural number. 0 is a whole number. We'll talk about that in a minute. But we could say something like that. So what numbers are between 0 and 6 on the number line? Well, what numbers are between 0 and 6 on the number line? Ran out of room here. Are the numbers 1 through 5 the numbers on the number line between 0 and 6? So we could do something like that. So how do we read this in words? We say the set B is equals always translates to is, sorry, the set of all x, and sometimes they use x's, but we're just going to use all x, such that, that's that vertical bar, x is an element of the natural numbers. A lot of writing. Why do we use set builder notation? This is too much to write. Element of the natural numbers. Oops, got too many ofs. And x is less than or equal to 5 and greater than, and you could have written this the other way. It's greater than or equal to 1 and less than or equal to 5. It doesn't matter. I'm getting messier as I get to the bottom of the slide. I don't need this brace there. Sorry, got my brain working. So that is the way you would write that, or the way you'd read it. I don't think you would typically write that, but that would be the way you'd read that set. Okay. So can we write this in roster form? The set A is the set of all x such that x is a natural number and x is greater than or equal to 2 and it's less than 8. So it's between 2 and 8, including 2, but not including 8. So what numbers would that be? Well, it'd be 2, 3, 4, 5, 6, and 7. We don't include 8. There's no equals here. So this is less than, not less than or equal to. So we're not going to include the 8 in the list. So what's the roster? The roster is what? 2, 3, 4, 5, 6, and 7. And again, when we create a set, when we write a set, either in set builder notation or in roster notation, we use the braces to the left and to the right of either the description, the condition, or the list to indicate that that is a set. That's how we mathematically indicate this is a set. Okay, subsets. Set A is a subset of set B if A is wholly and completely contained in B. So earlier we had a picture of a T set. So let's let A be the set that contains the teapot. Okay, and set B, what was that set? We had a tray, we had a teapot, and I'm just going to list cups. There are 4 of them, okay? So is A subset of B? And the answer is yes, because set A, the element teapot, is contained in the set B. So in this case, A is a subset of B. And we use that laid over U with a line underneath it to represent subset. So that is what that means. It means it's a subset. And I'm not going to get into all the particulars that there are subsets and there are proper subsets. If it's a subset, then it is completely and totally contained in the other set. So TA, which consists of the element teapot, is a subset of B because the set B contains that element. Right? If you put a line through it, it negates it. So that symbol that means subset, if you stick a line through it, it means it's not a subset. So if I have, again, B was our set of what? The tray, the teapot, I think teapot's one word, and cups. Then let's say A is a plate. Well, is A a subset of B? Do you see a plate as an element in B? So A is not a subset of B because A is not contained. The element in A is not contained in the set B. There is no element in B that says plate. Okay, so what if you have a set boat, train, and plane, and a set boat, train, plane, and automobile? Sounds like that movie, Planes, Trains, and Automobiles, which is one of my daughter-in-law's favorite movies of all time. So is A a subset of B? And the answer is yes, because A contains boat, as does B. A contains train, as does B. A contains plane, which as does B. So every element in A is in B. So A is a subset of B because every element in A is also in B. Now, what's not true? No, because B contains the element automobile, which is not in A. So if there's one element in the set that's not in the other set, then that set's not a subset. So B is not a subset of A because B contains the element automobile, A does not. If your set doesn't contain anything, it's called the empty set, and yes, that can happen. And we denote that either with braces with nothing in it or a circle with a line through it. That means the set that doesn't contain anything. Okay, number systems. We have talked about today the number system, the natural numbers, but there are infinite number of numbers on that number line that are not natural numbers, an infinite number. So let's start building our number systems. And as we build up through the irrational numbers, each number system prior is a subset of the next number system. Okay, so the natural numbers. The natural numbers are the numbers that we count with. They start at 1 and continue indefinitely to the right. But, and my grandson has already learned the harsh reality of none, 0. So we have to have the concept of 0 to work anywhere in mathematics. So if we take the natural number system and we add the number 0 to it, we get the number system called the whole numbers. So the whole numbers are the natural numbers plus 0. So the natural numbers are a subset of the whole numbers because the natural numbers are completely contained inside the set of whole numbers. Okay, as we've discovered in the last week or so, we need the concept of negatives, especially if you measure temperature in Celsius, which we'll talk about at 11 o'clock. So or if you've ever drawn your bank account, do you learn the concept of negatives pretty quick? So we need negative numbers, and those are numbers that are less than 0. They're smaller than 0. So we add the negative numbers to the whole numbers, and we get the set that are called the integers. So the integers are the set of whole numbers and their negatives. So you have the whole number 0 through infinity to the right, and then you add the negatives. So the negative of 1 is -1, the -2 is -2, et cetera, et cetera. So they continue indefinitely to the left. So the integers are the set of whole numbers with their opposites. Okay, now there are an infinite number of numbers between two integers on the number line because we have fractions. And as soon as we talk about fractions, people get all weirded out. And it's you deal with fractions every dadgum day, every dadgum day, every day, every day. You can look at a tape measure and see you got a half an inch, and know that if you get another half an inch, you got a whole inch. You do that kind of thing all the time. So we can take these integers and write them as ratios, one integer over the other, as long as the denominator is not 0. You can never have a denominator of 0. Never, ever, ever, ever. Cannot have a denominator of 0. So if I write a ratio of two numbers where the two numbers are both integers, we write them as a fraction and the denominator is not 0, that's the set of rational numbers. It's a ratio of the integers, so we call them rational. Okay, so rational numbers are any number that can be written as a fraction. Now, that means intellectually, I guess, I don't know what word I'm looking for, you could write that as a decimal. So you can write rational numbers as decimals that either terminate, so like 0.25, or decimals that repeat, like 0.33333333. So if it's a rational number, it's a decimal that terminates or repeats, you can write it as a fraction. Well, there are a whole infinite number of numbers you can't write as fractions. So in their see, mathematicians are so fun. In their infinite wisdoms, they said, if it's not rational, it must be irrational. So if a number is not rational, it is irrational. I didn't make it up. So what are irrational numbers? Irrational numbers are numbers you can't write as fractions. So they're either their decimal doesn't terminate or it never repeats. And there are an infinite number of numbers that are irrational. Pi is an irrational number. It never terminates, it never repeats. The square root of 2 is irrational. Those numbers you cannot write as fractions. Okay, how much time do I have? 1 minute. All right, so if I take the set of rational numbers and I join them with the set of irrational numbers, join them together, union them together, I get the number set that are called the real numbers. And that is the number system that we use 90% of the time, 99% of the time in mathematics. So the real number system is every single solitary number on that number line. And there are an infinite number of numbers on that number line. There are an infinite number of numbers between 0 and 1 on that number line. Some are rational, some are irrational, but there are an infinite number of numbers on that number line. So as I said, I'm out of time, but each of these number systems we built, we took the natural numbers, added 0, got the whole numbers, added their opposites, got the integers, wrote them as ratios. So the ratio of integers gave us the rationals. Then we get the whole another set called the irrationals. And we join those two sets together and we get the real number system. Okay, are there any questions? Because I am done. No, no questions? Man, I'm good then. Okay, I'm going to end the meeting and I'll upload this recording probably around noon, and I will send out the YouTube link. If there are no questions, I'll see you in the other meeting in about 10 minutes. See you there. Bye-bye.